Sorry. All right, so yeah, rank these from the worst nucleophiles to the best nucleophiles. All right, so for our first row here, actually sort of already in our correct order here. And the trend is the same as what we see for basicity. The worst nucleophile would be water. It doesn't have that net negative charge. Remember, a good nucleophile will have a negative charge associated with it, will be really electron rich. And then comparing the fluoride ion and the oxide ion, again, it's the stronger base that's the better nucleophile. The hydroxide ion is a stronger base and thus a better nucleophile. Let's skip down to the third row here. If we put this in order, it's sort of already in order, so I had to mix it up. But again, we'll see that the trends are the same thing as we see for basicity for our nucleophilicity. HF, again, it doesn't have that net negative charge, so it's going to be the worst nucleophile. And then if you're comparing hydroxide and that carbon with a negative charge, the carbon ion, remember that carbon ion is super PO'd to have that negative charge associated with it. It's going to grab a proton from anywhere it can. Likewise, it's going to react in terms of our nucleophilic reactions wherever it can. So same trend as we see for both of these categories, same trend as what we see in our basicity. Where things get mixed up is in this middle group here, because now we're comparing down a row, right? All of these live in the same column on the periodic table. And so it's actually the largest that's going to be the best nucleophile. So in this particular case, it's actually going to be the opposite of what we see for basicity, right? The size factor dominates here. And so even though basicity trends where the fluoride ion is the most basic, it's kind of the opposite of what we see here. Let me use a different color, actually. Right? So bottom line is, roughly speaking, good bases are also good nucleophiles. The only difference being when you take size into consideration, the larger ions tend to be better nucleophiles than the smaller ions. All right? The other thing we talked about was leaving groups. Okay? What makes a good leaving group a good leaving group? Where do we have that? Okay, so good leaving groups are now the opposite sort of trend. These are bad bases, right? So nucleophiles are good bases, leaving groups are bad bases, right? So the worst leaving groups are these strong bases, the hydroxide ion or nitrogen when it has a negative charge. Right? Another thing that will never be a leaving group would be a carbon ion. That's a terrible leaving group because it's such a strong base. But things that would be good leaving groups, things like water or the iodide ion, things that are bad bases. Okay, so trends the opposite of what we saw for with nucleophiles, right? So bad bases are good leaving groups. All right, so where are we going with this? These reactions, the first ones we're going to do are called substitution reactions. Okay, and so what we're going to see in these reactions is, for example, Right? This would be an example of the type of substitution reaction that we're going to see. We started out with an iodine on our molecule. That got displaced, and it was substituted out for this hydroxide ion that is now attached to our molecule, right? So you're substituting your functional groups, swapping out one thing for another thing. Those are substitution reactions. We said that the hydroxide ion, this is playing the role of the nucleophile in this reaction. What role is the iodide playing? The leaving group, right? It's the thing that's getting kicked off. So that is our leaving group. Okay? And then the thing that's getting attacked by your nucleophile is what we call an electrophile. And that would be that carbon right there, the carbon at the base where that new bond is formed. That's our electrophile. Okay? So, how do we do these reactions? We're going to look at the reaction mechanism for these substitution reactions. All right, so again, I'm just going to use the same one, sort of just recopy it so we can draw our curved arrows on there to represent the reaction mechanism. Right? By reaction mechanism, I mean putting in those electron pushing arrows. Okay? So, what's going to happen is what we call like the nucleophile attacks, all right? Meaning that this negative charge is going to come and attack that electrophile. Nucleophiles attack electrophiles. The base of your arrow will always be at the nucleophiles because those are the electron-rich species. Remember what this arrow is sort of representing. I'm taking this pair of electrons from my nucleophile and I'm dragging it over to this carbon atom here. Does this represent a new bond that's being formed, or is a bond being broken here? This is actually the formation of a new bond. Anytime you're connecting two things that didn't used to be connected, that means you're making a bond between them. So this arrow right here would be bond formation. I'm creating the new carbon-oxygen bond. All right, and I'll actually be good and put in lone pairs. In particular, this pair of electrons, come on, that used to be on this hydroxide ion, that's what's going to make up my new carbon-oxygen bond. That's what that arrow is representing. A formation of a new bond. I'm taking that pair of electrons and dragging it over to that carbon atom, making a new bond. Okay? Can anybody see what else I'm going to have to do here? I've made this new bond. What am I going to have to do next? I got to break that old bond as well, right? I got to kick off that iodide ion. And so that would look like this. This pair of electrons is now going from that bond to being associated just with that iodide ion, right? This represents a bond being broken. Right? Again, you want to think of these arrows as grabbing pairs of electrons and dragging them someplace, right? So I'm dragging this pair of electrons that used to be a bonding pair of electrons, and I'm putting it only on that iodide ion. So again, my products here would be and this pair of electrons that used to be in this carbon iodine bond are now sitting only on that iodide ion. And I guess I can color my purple ones too. What's up?
So unlike the other situations, like in previous chapters, these arrows, they can go against each other?
So they're not going against each other, right? So you never have the two arrows pointing at the same atom. So you have one arrow that's pointing at the carbon atom, and then that other arrow is moving away from the carbon atom. Right? So they are pointed in opposite directions. The heads of those arrows, if I were to kind of follow this along, it's like this way and then that way. Right? They are pointed in different directions. Yeah, so like one of the ways, again, how you would know, you'd be able to spot that, you know, so oftentimes it's like, okay, I see the bond that's being broken, and it's easy to switch around which way your arrows are pointed. What would be wrong, what I mean by pointing in the same direction, would be something like this, where the heads of your arrows are meeting at the same atom. That would not be correct. So they want to be pointed in opposite directions. Does that make sense? Okay. And so yeah, and again, sort of like what you can ask yourself with these reaction mechanisms are, where are my electrons coming from in the new bonds that I made? Again, in this case, it's this lone pair on the hydroxide ion that's created this new carbon-oxygen bond. That's what I colored in purple, right? What used to be a lone pair is now a bonding pair of electrons, right? Remember, bonds are also just made of electrons. Lone pairs are made of electrons, right? We represent one as little dots and one as sticks, but they both represent electrons. Likewise, I can follow where that blue pair of electrons went as well. It used to be in this carbon-iodine bond. I've now dragged it on to being associated only with the iodine arrow. So it goes from being iodine ion. There it is, iodide ion. So it goes from being a bonding pair of electrons to a lone pair of electrons. Okay? So this is a substitution reaction, and in fact, we have an even fancier name for it, which would be a nucleophilic substitution reaction. And actually, we represent this. This is what we would call an Sn2 reaction. So the N is because it's a nucleophilic substitution reaction. The S, because it's a substitution reaction. And the 2 comes from the fact that there are two, what we call, because there are two species that are involved in that first step of the reaction. Both the hydroxide ion and our organic, what we call an alkyl halide. This would be 2-iodobutane. Anyways, both of these are involved in the first step of our reaction. Okay, so that's what that 2 stands for. We're going to see Sn1 reactions as well, where there's only one species involved. Okay, but the 2 in this, it's a Sn2 reaction because you have these 2 species that are involved in this first step. The hydroxide ion does the attacking at the same step that your leaving group leaves. Right? That happens all in one shot. Okay? An Sn1 reaction is also a nucleophilic substitution. But an example of that would be something very similar to what we just saw. For this particular reaction, I have water that's playing the role of my nucleophile. Okay, water is a weak nucleophile. We'll talk about why these reactions require weak nucleophiles here in a second. I again have my iodide ion playing the role of the leaving group. And I again have that carbon that's at the base of that iodine. This is going to be my electrophile. Okay? But the 1 is because there's only one species in that first step. All right, and so what does that mean? The first step of this reaction actually doesn't involve the nucleophile at all. It's just the leaving group getting kicked off. Okay, so the first step, unlike our other ones where the nucleophile attacks in the same step as that leaving group leaves, in Sn1 reactions, the leaving group just kind of falls off. Okay, so my first step here would be creating this carbocation. Okay. Right, just like we saw before, that pair of electrons that was in that bond is now getting broken and put onto only that iodide ion. Right? And the carbon that's left behind, it has a positive charge associated with it because it got a pair of electrons taken from it. Right? And we can also sort of just note that the balance of charges has to be here because I've created this negatively charged iodide ion. That means I also have to have a positive charge on there as well. Okay, so in our Sn1 reactions, that first step, step 1, is the loss of our leaving group. Okay, there's only one species involved in that first step. That first step is that leaving group just falls off. The second step is now we have our nucleophile doing its attacking. All right, so one of those lone pairs on oxygen is going to hit that positive charge. Everybody take a second and see if you can't draw me the product of this step here. If we can't, let's see if we can follow our electron pushing arrows. What's going to be the product of this step of my reaction here? I'll give you a hint. We're not quite here yet. We haven't quite made it to our products quite yet. All right, so first of all, am I making or breaking a bond here? I'm making, right? I'm connecting two things that didn't used to be connected. That's going to be making a new bond. Specifically, I'm making a new bond between carbon and oxygen, right? The base of my arrow was at that pair of electrons that's on oxygen. So boom. The only thing here is I don't yet get rid of those two protons, those two hydrogens that are on that water molecule, right? They didn't go anywhere in this step of my reaction. So I've created this new bond, but I still have those two hydrogens. Let me draw them explicitly, actually. And what do we know about an oxygen that has 3 bonds? How many lone pairs does it have? Just one. And what's the formal charge on an oxygen with 3 bonds? +1. All right, so again, conservation of charges. That positive charge didn't go anywhere. All right, that's why that little cheat sheet of formal charges, number of bonds, is really helpful, because just by recognizing the fact that there are 3 bonds on this oxygen, I know that it has that positive formal charge. You can again convince yourself of that because our conservation of charges. Okay, so then, obviously, if we're going to play spot the difference, we got one more step to get to our actual products here. What am I going to have to do?
Get rid of a hydrogen.
I got to chop off one of those hydrogens, absolutely, right? I'm trying to turn this into this, right? So I'm going to need to pull off one of those hydrogens. And what's going to do it is that iodide ion that I created. It's going to reach out and grab that hydrogen and break that oxygen-hydrogen bond. Okay, so we got a lot to unpack here, but these are our two substitution reactions. Okay, let's just sort of practice making products here. What's up?
I may be getting ahead of myself, but how do we know which substitution to use? Like,
Yeah, we'll get to that in a second. Right now, let's just predict our products, right? We're just swapping out functional groups here because actually predicting the products is the same regardless of our mechanism. But we will talk about what goes what. Count your carbons. Easiest way to double check. Shouldn't have any new carbons, shouldn't lose any carbons. So step one in terms of predicting products, we're just going to swap out our functional groups, right? So I'm going to make sure that my product in this first one has 1, 2, 3, 4, 5 carbons. So I'm going to start there. And I'm going to replace my functional group on that last carbon there. Okay? In this first reaction, let's label the nucleophile. Which one is the nucleophile? Yep, so this one is my nucleophile. All right, point to the electrophile in this reaction.
it'll be the 5th carbon.
It'll be this one right here, yep. All right, and then the iodine, so this is a little weird, but bear with me here. The iodine is playing the role of that leaving group, right? If you were asked what is the leaving group, you would say actually it's the iodide ion. You sort of identify the leaving group as what it is after it's already popped off. So that iodine is what's being the leaving group. That's what's getting kicked off, right? But if I asked you for what the leaving group was, you would say it's that iodide ion, right? We identify the leaving group as the species after it's been kicked off. So it'd have that negative charge on there. All right, so now let's go ahead and do this reaction here. Again, I want to make sure that I have my 6 carbons in my ring, my cyclohexane, and I'm going to swap out the functional group on that top carbon with that OH group. Okay. So again, take a second to identify the nucleophile, the electrophile, and the leaving group in this reaction. And my nucleophile is the thing doing the attacking. The electrophile is that carbon that gets hit by the nucleophile. And my leaving group is that chloride ion. All right. This next one is a little bit of a trick question here. Okay? Obviously, it's very tempting to, you just do your substitution, right? Boom, 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 with the fluorine on there. All right? The problem is, what's the deal with that hydroxide ion? Is it a good leaving group or a bad leaving group? It's an awful leaving group because it's such a strong base, right? So this would be my products if this reaction occurred. Okay? The problem is that this reaction would go the other direction, right? In fact, I wouldn't create these products. If I started out here, I would have, because this is a bad leaving group. And this really isn't a great nucleophile. So in that sense, this reaction would trend towards the reactants side of, if I was looking at this, thinking about this as being in equilibrium here, this equilibrium would very greatly favor the reactants side. I would not get any products out of this. Because over here, I have a strong nucleophile. All right, so that was a little bit of a trick question here. But the bottom line is we see how our functional groups get swapped. We can identify our nucleophile, our electrophile, and our leaving group in our reactions. So now let's address this question of which goes on, what undergoes what mechanism here. Okay? The key to the Sn1 reactions is the formation of this carbo cation. Right? That's that key first step where that leaving group just falls right off, forming our carbo cation. All right? Only tertiary carbocations will form. Right? What do I mean by tertiary? What am I counting when I determine whether a carbon is primary, secondary, or tertiary? The amount of carbon neighbors, right? So this carbon right here, this carbocation is a tertiary carbocation because it has 1, 2, 3 carbon neighbors. So basically, I will only get carbocations that look like this. I will not get secondary ones or primary ones. These do not exist. What's up?
And that's why in that first reaction for the SN2, it wasn't wasn't broken down into more steps.
Exactly, right? Everything happened in one shot. The leaving group left at the same step that the nucleophile attacked. You never had this carbocation that was formed. All right, so yeah, exactly. If we go back and look at our other reaction mechanism here, these two happened all in one shot. There was none of this secondary carbocation that was formed. This doesn't occur here, right? We don't get anything but a tertiary carbocation. Okay, so now let's take a look at a bunch of different molecules and identify whether they undergo Sn1 or Sn2 reactions. All right, so let's do this first one. Sn1 or Sn2? Sn2, right? So we can chop off that leaving group, whoops, put that positive charge down, and then ask ourselves, is this a tertiary carbocation? In this case, it's not, so it has to be an Sn2 reaction. All right, what about the next one, this one down here?
Sn1.
So this one, if I chop off that leaving group, I would indeed have that tertiary carbocation. So these are Sn1 substitution reactions. All right, and what about this third one down here?
Sn2.
So this would be Sn2. All right, so this would also, Sn2, here we would have a tertiary carbocation that would form. So that would be an Sn1. And then this last one, it's just a methyl. So it would be Sn2 as well. All right, so we're looking at how many carbon neighbors are at the base of that halogen. Notice that the starting point for these reactions are going to be typically alkyl halides. Right? Those halogens are great leaving groups. They can get kicked off pretty easily. So there's the starting point for these reactions. All right, so one more thing with regard to these substitution reactions. And this is what we call stereochemistry inversions, an inversion of stereochemistry. What do I mean by that? So, if we have a structure where we're explicitly representing one of our bonds as being either a dash or a wedge. So for example, this one here. What does the wedge mean? Where is it pointed? The wedge means it's like pointed out at you, right? And then the dash means that it's pointed into the page. Okay? when these reactions occur, if I have a, let's use my nucleophile here, is this going to undergo an SN1 or an SN2 type reaction? SN2, I would only have a secondary carbocation, so this will be SN2. So because this nucleophile attacks in the same step that my leaving group is kicked off, you have what's called an inversion of your stereochemistry, which really just means that if that iodine group is pointed out at you, that new functional group is going to be pointed into the board. Okay, so when you have this substitution, you have an inversion in your stereochemistry. The wedges would become a dash. The dashes would become a wedge. All right, so let's do another example here. I want you guys to predict the product with the proper stereochemistry. Right, so again, what was used to be a dashed bond, now when I have my substitution reaction, is going to become a wedged bond here. What's up?
If it's SN1, does the same thing happen?
We'll get, yeah, no, and we'll get to that in 1 second, right? So both of these are SN2 reactions. SN2 reactions lead to an inversion, right? You're swapping your dashes and your wedges. If we had instead something like this, this would undergo an SN1 type mechanism. When SN1 reactions occur, there is no inversion. All right, so actually, if I were to do my products, I would have a mixture of both different possibilities. One where that new functional, whoops. Use a different nucleophile here. One where my new nucleophile is in one position and the other, right? So you get both possibilities. Both on your new functional group is both on the wedge and on the dashed bond. You would get a mixture of both of these. Cool, all right, so that's our substitution reactions, and we have these two mechanisms, right? The SN1 are for the more highly substituted ones, where we have a tertiary carbon at the base here. SN2 are for if you have primary or secondary carbons at the base of your leaving group. With the SN2 reactions, you have an inversion in your stereochemistry when you have substitution. And SN1 you don't. You're going to get a mixture of both possible products. Cool. All right. So I'm going to take a second to hand out back